good. So we'd like to begin our second tutorial for the day. Okay, and so as I set the context, right, is ultimately within a lot of these kind of systems, right, safety. So people talk about human-robot collaboration for manipulation, right? But really, until you address the certification issue of achieving safety, right, then it can be really hard to push that. So in those cases, you want to be able to provide some guarantee in terms of safety of motions and then the safety reaction. So the idea of bounding risk at all these levels, right, is really important. Here we'll talk about motion, but you really can talk about it for just about every tutorial that you see. You can talk about what are risk bounded versions of that, right? So Phil had mentioned that yesterday in terms of being able to look at multi-vehicle routing. I don't know, but being able to think about risk bounded versions of that. Bob talked about simple temporal networks to kind of model uncertainty with set bounded approach. You want risk bounded versions of those. So policy simple temporal networks is a form of that. So we'll talk about probabilistic planning and AO star and LAO star, and there are risk bounded versions of that. So there's a risk bounded AO star. There's an algorithm dual, which is a risk bounded version of LAO star. Right? So here we'll only be able to kind of give you one representation of that, but then you can then generalize those lessons. There's a very rich area. Now, to also mention is once you have a risk bounded approach, and that's been explored a lot in motion planning, then there's this question about is you have realistic distributions, right? And you have a realistic dynamics, right? So the idea is that, well, we need to be able to kind of go beyond linear. Then when you deal with nonlinear convex, then that makes risk bounded reasoning all the harder. If you want to deal with distributions which aren't just Gaussian, right, then that becomes challenging as well. So Ashkan will be touching upon all those issues.
Yeah. Thank you. So as Brian said, this last talk is on risk-bounded motion planning, and I want to start with this question that what is risk? How do you define risk in planning? Any thoughts?
The probability that something would occur as planned, would not occur as planned.
Right. So in short, risk is defined as chance of failure in plan. So why do we need to care about chance of failure in motion planning? On Tuesday, you saw a set of nice tools for motion planning. Using these motion planning algorithms, you can make robots run, fly, swim. You can launch the spaceship. You can even make them to do a backflip. So if you have such powerful techniques, why do we need to look for risk-bounded version? Okay, this is one answer, but not the right. Safety. Yes. The main problem is the safety. So most of these techniques has a big assumptions. They assume that we know the state of the world, but asking for a state of the world is too much. We have too many sources of uncertainty. We have sensing disturbances when we are localizing the robot and obstacle. We have control noises, for example, the wind disturbances for drones. We have unknown, rough, uncertain terrains for walking robots. So simply, we do a trajectory optimization to drive a robot from a given state for a stable pose, for example, for a stable pose for an Atlas robot, or a stable pose for a spaceship. But because of uncertainty, robot deviates and ends up in an unstable pose and fails. And even if we have a precise sensors, even if we know, if we have prior knowledge about the environment, the intention of the other players are also uncertain. For example, when we are driving, the decision of the other drivers are uncertain to us. So to deal with uncertainty, we are going to use risk-bounded motion planning algorithms in this talk. But before we do this, so we want to know what are other options to deal with uncertainty. In general, we have two sets of options, robust techniques and risk-bounded techniques. In robust techniques, if we are doing planning under uncertainty, the obtained plan should be valid for all possible values of uncertainty. Let's see how it works. Consider this a simple motion planning scenario. We want to drive robot from a start position to a goal region. We have a turtle bot that plays a role of a fixed obstacle. So we don't have any uncertainties. So we can call many different motion planning algorithms like RRT star, PRM, or trajectory optimization, construct our path to the goal. Now consider next scenario. This time, TurtleBot plays a role of moving obstacle, and its location is uncertain. We only know that the obstacle moves between these two given points. Now, if we want to use robust techniques to construct a path, what should be the path look like? How should we construct the path? So from robust approach, the obtained path should work for all possible of uncertainties, where here is the location of the TurtleBot. So it means that we are allowed only to use the left side of the room to construct a path. Right now, no matter how this obstacle moves, we are always safe. So what is wrong with this kind of reasoning? This robust reasoning. No, we don't have all information about the moving obstacle. We only know the range of uncertainty. It is, yes, it could be.
You assume that the robot is moving right only?
Pardon?
You assume that the robot moving obstacle is only moving to the right hand side?
No. So let's look at the next scenario. This time, the obstacle moves from that side of the room to this side. Right now, the problem is infeasible. There is no path that is valid for all possible values of uncertainties. No matter how we construct the path, we can find a location for the obstacle that collides with our path. So from robust techniques point of view, this problem is infeasible, right? Even if we replace the TurtleBot with a real turtle that takes 10 days to travel from that side to this side, this problem is infeasible. There is no path, so too conservative. So in general, robust techniques result in too conservative because we want the plan work for all possible scenarios of the uncertainties. Or in other words, we want to plan for worst case scenario. So what is this worst case scenario? For example, assume that we are driving. Should we assume that all other drivers are drunk and distracted by their phones? Planning for this situation will result in too conservative and poor plan. So this is where risk-bounded approaches step in and suggest that, okay, let's not only look at the uncertainty set, but also the frequency of each values of the uncertainty. How frequent is to see obstacles in this side of the room? Frequency of the uncertainty means probability distribution of the uncertainty. So if we look at the probability distribution and if we get lucky, we will see that there is a small chance that we observe robot in this part of the room. So we can use this space and construct the path to the goal. But since still there is a non-zero chance of observing obstacles, there's a non-zero chance of collision. So there's a non-zero chance of failure for this plan. In this talk, we are going to look at tools to minimize this chance of failure, or we bound this chance of failure by given predefined value delta that we call it risk bound. So in summary, if I want to compare the risk-bound approach and robust, it is all about probability versus possibility. In possibility, in robust, we only have two outcomes, failure or success, 0 or 1, just two outcomes. But on the other hand, risk-bounded versions offers us 0, 1, and whatever is between. Not only we can fail or success, we can also decide the degree of this failure and the success. So we have more freedom, and this freedom will result in less conservative plans. Okay. Any questions so far? And if you have any questions, please let me know during the talk. So now we know why do we need risk-bounded approaches. Now let's come up with a nice mathematical formulation. So in risk-bounded motion plannings, we assume that first we are given a continuous state space model for a robot. In this model, X represents a vector of states. For example, this vector could represent position and velocity of a vehicle, or joint angles and angular velocity for a manipulator or a walking robot. And since we have uncertainty, I model uncertainty with the omega with some known probability distribution. Given this dynamic and given the current state and the current control input, we can find the states for the next time step. Next, we are given an unsafe region in state space that I call an obstacle. This region is described by a set of inequalities. For example, if these inequalities are described by linear constraints, we are going to see some convex polytope in state space, and where each edge is described by one of these linear inequalities. Or these inequalities are described by polynomials, where we can, in general, describe more complex and non-convex region. For example, that non-convex region is described by one polynomial inequality. So given uncertain dynamical system and given obstacles, risk at time k is defined as this probability that state of system at time k collide with obstacle. Now, in risk-bounded motion planning, we are looking for sequence of the control inputs such that we drive a robot to a goal region with respect to these chance probabilistic constraints. We want to bound the probability of collision with obstacle by given delta k risk bound. Or equivalently, we want to make sure that probability of the success, probability of remaining in safe region is greater than 1 minus delta k. We know how to deal with deterministic constraints. But here we want to see how we can actually evaluate these probabilistic constraints. To evaluate these probabilistic constraints, we have to go through two steps. First step is uncertainty propagation, and the next one is probability calculation. Let's see how uncertainty propagation works. So we are given nonlinear dynamics that describes the position of the airplane, and we are also given a control input. The control input is the velocity and the yaw angle of the airplane. Using this control input, we can drive the plane to a goal region, avoiding the obstacle. Now assume that we have uncertainty, wind disturbances, control noises. I model them with the omega 1, omega 2, and omega 3 and 4. They have some probability distribution. Now, because of this uncertainty, plane will deviate from the given nominal trajectory. If we repeat this experiment over and over, we will see these trajectories for plane, the trajectories that are disturbed by the uncertainties. If we look at these trajectories at discrete times, we are going to see such patterns. These patterns show the possible locations for the airplane at each discrete time. These patterns are different realization of a random variable. So we can use numerical approach and come up with a probability distribution associated for these samples. So it means that since we have a probabilistic uncertainty at each time k, states of the system are also random variable and has some probability distribution. And to evaluate this probabilistic constraint, we have to find this probability distribution. But in general, we don't have any closed form solution to describe this distribution except for particular cases. For example, consider this case. Here, this is a plane scenario. I redefine the input so that we can get a linear dynamics. Right now, the input is velocity in x and y direction. I assume that uncertainties are Gaussian. In this case, this is how the uncertainty propagates, the uncertain location of the airplane. If we look at these uncertainties, we will observe Gaussian distribution. At each time k, the states of the airplane has a Gaussian probability distribution with different mean and different covariance. And we can come up with a closed form formulation to describe this mean and covariance. So in general, if you are given a linear dynamics with Gaussian uncertainty for initial state and also for uncertainties, at each time k, states of the system will have a Gaussian distribution whose mean and covariance are described by these two equations. Based on this, the mean at time k plus 1 can be described by the mean of state at previous time, input, and the mean of the noise. And the covariance at k plus 1 can be described by the covariance of the states and the noise at time k. So we have a nice formulation to propagate the uncertainty when we have a linear dynamics and Gaussian distribution. Now, assume that we are given probability distribution for states, Gaussian or non-Gaussian. In next step, to calculate this probability of failure, from the definition of the probability, we need to find this integral with respect to the given probability distribution over the obstacle region. And this obstacle is in general non-convex and it's nonlinear and complex. So we don't have any closed form solution in general to find this integral, and this requires a multivariate integral techniques. But if we assume that the given distribution is Gaussian and the obstacle is defined by linear inequalities, we can come up with a closed form solution for this probability. Since the summation of Gaussian distribution is also a Gaussian distribution, we can define a new variable zy based on the linear constraint. And then we can find its mean and covariance based on the mean and covariance of the state. By doing so, instead of evaluating this multivariate probability, I can evaluate this univariate probability based on Z1. And since it's a Gaussian, I can write its probability based on the CDFL of the standard normal distribution. To find this probability, I just need to find that value, b minus mean of the z divided by covariance, and then I need to look for the CDF and get the probability. So we have a closed form solution to calculate the probability when we have a linear constraint and Gaussian distribution. So in summary, to be able to evaluate the chance constraints, we have to go through uncertainty propagation and probability calculation steps. And in risk-bounded planning, we are trying to find control sequence such that to shape this probability distribution such that the overlap of these distribution and obstacles that defines our chance of failure, chance of collision, such that this failure becomes less than our risk bounds. To do this, I'm going to look at several approaches. The first set of approaches, I will assume that we have a Gaussian linear system with linear obstacles, since we know how to propagate uncertainty. And in the next set of approaches, we will look at more general cases with nonlinear dynamics and arbitrary distribution. So let's look at the first set. In the first approaches, I'm going to come up with a risk-bounded version of trajectory optimization, RRT star, and PRM, three popular motion planning algorithms. So let's first start with chance constraint trajectory optimization. We know how to solve deterministic trajectory optimization problem. You saw this on Tuesday. So in deterministic case, we are given an initial state for robot, and we are looking for a sequence of the control to minimize a cost function that usually represents energy function with respect to dynamical constraint and hard constraint on safety and constraint on the final state. In the chance constraint version, we are given the initial distribution for state and distributions for uncertainty, and we are looking for a sequence of the control to minimize the expected value of the cost function with respect to dynamical constraints and probabilistic constraints on safety and expected value constraints for the last state. And since we assume that everything is linear, we have a linear dynamics, Gaussian distribution, linear obstacles, so we need to solve that linear stochastic optimization. Now, the main idea is to replace that probabilistic constraint with linear deterministic constraint in terms of the mean and the covariance of the distributions. And we know how to propagate and get those mean and covariance. So by doing so, we are going to get a deterministic linear optimization, and we know how to solve it efficiently. For this, so we saw that if we have a univariate Gaussian random variable, we can describe the probability in terms of the CDF. Now, if we are given a chance constraints in terms of the univariate Z and a linear constraints, to satisfy this constraint, using that result, the mean and the covariance of the univariate random variable should satisfy that linear constraint. So based on this linear constraint, the mean Z bar should be greater than B, that comes from the linear constraint, plus some safety margin C, where the safety margin is described by the covariance and also risk bound. Then using this result, and also by univariate representation of the linear constraint, we can show that to satisfy this given probabilistic constraint in terms of one linear inequality, the mean and the covariance of the state should satisfy this linear constraints. Based on this constraint, the mean of the inequality, the left-hand side, should be greater than B, which comes from the constraints, plus some safety margin C, which that safety margin is described by the covariance of the states and also risk bound. And we know how to find this covariance and the mean. So given this probabilistic constraint, we can come up with this linear deterministic constraint in terms of the mean and covariance. Now, assume that we are given a linear obstacle described by a set of linear inequalities. So what is the safety constraints for robot? Assume that everything is deterministic for now. So for safety, robot should stay out of the obstacle, or robot should stay in the other side of each edge. So in this case, robot for this obstacle has 4 options. Robot could be in the other side of the first edge with introduce these linear constraints, or robot could stay on the second region on the other side of the second edge, or robot can stay on the other side of the third and the fourth edge. So this obstacle introduced 4 disjunctive constraints. Robot has option. It could stay in this region or in that region. Now, since everything is probabilistic, we will going to look at the probabilistic version of those linear constraints. So we are going to get disjunctive probabilistic constraints. And from the previous slide, we know how to replace this probabilistic constraint with the deterministic one. We can replace each of these constraints with linear deterministic in terms of mean and the covariance of the distributions, plus some safety margins. If we plot these new inequalities, we will see something like this. So this is our original obstacle. The red lines are the new obstacles. It is a new obstacle which its size depends on the safety margin. As safety margin increases, this obstacle will increase. So right now, if the expected value of the distribution, the center of these circles, it stays out of this safety margin, the chance constraints are satisfied. So in trajectory, in chance constant trajectory optimization, chance constraint at each time will introduce a new obstacle, and then everything becomes deterministic. We just need to make sure that the expected value stays outside this safety margin. That's simple. As the covariance, this distribution increases, safety margins will increase, and we are going to get a larger and larger obstacle. So in short, to solve this trajectory optimization, we need to solve this linear deterministic optimization involving disjunctive constraints. And we can solve this problem efficiently. We can, for example, use big M formulation and reformulate it as a mixed linear integer program, MILP. And we can call, for example, Groby and solve it efficiently. So before I get to some simulation results, here I assume that at each time k, we know risk bound. Yeah. Pardon? Groby is a solve optimizer that we can solve linear programs and MILP. Yeah, you can call it from MATLAB or other softwares. So we can efficiently solve the MILP and linear optimizations. Okay, so here I assume that we know delta k, we know the risk at time k, but usually we are given a risk bound for a whole mission. We are given delta for a whole mission, and to find the delta k's, the risk bounds for each time k, one option is to uniformly allocate risk between different time steps by dividing the delta by t, which knows the number of these steps for a whole mission. And if we have multiple obstacles, we can again uniformly allocate risk between the obstacles by dividing the delta k by n, which n is the number of the obstacles. But the other option is to use non-uniform risk allocation. In this case, we assume that delta ij, risk bound for obstacle I at time j, is unknown, and it's an optimization variable. And optimizers should decide these risk bounds with respect to this constraint. The summation of the all risk should be greater than given risk bound.
Why can you not take the same risk bound for all the steps every time?
Pardon?
So we have calculated a risk bound that is accumulated over the entire path, right? Why is it not, why do we have to allocate the risk separately?
So we are given delta, but in the optimization that you saw, we needed delta k. We need to find how much risk we want to spend at time k. So we need to get delta k from delta.
And it is incorrect to take the same delta as delta k.
Pardon?
It is incorrect to take delta k.
Yeah. So if we assume that at each time k we want to use delta, then if we find a risk for whole mission, it could be a disaster. It could be something large. Any other question? Okay.
So I thought you were asking a little bit different question, which is why not just use the uniform risk allocation, right? Which is to take the same risk at every point.
Yes.
Huh.
And the reason why is that turns out to be fairly suboptimal, right? What you want to do, so there are places, kind of the classic example that we'll have is when you turn a corner, right? Where if you're trying to hit your destination stats, it's possibly going to clip the corner, right? Because that speeds you up a lot, right? But when you're going straight down the hallway, it doesn't make sense. So you kind of going up to the wall. So in those cases, go straight down the hallway in the middle, don't take very much risk, and then spend your risk when you flip the corner. The cumulative risk is the same, right? But you allocated risk where you get the greatest benefit. So the whole idea behind risk allocation is uniform risk is simple, that's what people did before, but it wasn't that great. So allocate your risk and you can do a lot better.
Yeah. So if at time k there is no obstacle around, I don't need to spend risk, so we can save it for more challenging scenarios. Delta. Yeah, we should know the mission length. We assume that we know t. So if you want to work with the fixed delta, then at each time k, and if you want to remain uniform, we're going to have a less option to risk. So that's why we like to work with the non-uniform case.
What if there are two obstacles close to each other? Their risk bounds will overlap.
Yes, then we will see in the next scenario, yeah.
Okay.
Let's talk. So in this scenario, so we want to drive a robot to get to the goal region. So the solid line shows the obtained path for non-deterministic case, which is optimal and the shortest path. So when we have uncertainty, because of those safety margins around the obstacles, the obtained path tries to get far from the obstacle. And as we decrease the risk bound, the obtained path, the blue one, for example, tries to get farther. So the reason is this: by decreasing the risk bound, the safety margin increases, and those safety margin blocks this area between the obstacles. So you point. So we are not allowed to take that way. So that's why it decides to take the longer path to get to the destination. So in general, there's a trade-off between optimality and risk. If we want to be optimal, we need more risk. And in similar way, we can add a different constraint. For example, here I have two rovers, and I want them to go to the goal region. We have several regions to go and visit and take samples, but we don't know the order. The optimizer should find the order of the visit. Each of these locations will add a new disjunctive constraint to the problem. For example, a robot at time k has this option of visiting region 1, region 2, and so on. So this will add new set of disjunctive constraint, and then in similar way we can come up with the probabilistic version and solve the problem. So in these problems, the optimizer decides that to meet the chance constraint, the rover 1 should go and first visit region 1, 3, 4, 6, and the rest of the regions should be visited by the rover 2. So what if we have too many number of obstacles? So each edge of the obstacles introduces one constraint to problem. So if we have too many obstacles, we are going to get a large optimization problem. How we can reduce the size? So in this case, when we have too many obstacles, instead of working with obstacles directly, instead of writing the safety constraints based on obstacles, we can first look for safe regions and construct some connected safe region, and then state the safety constraints in terms of the safe region. So here, in similar way, a robot has the option of being in the safe region 1, 2, 3, and this will introduce a disjunctive constraint, and then we can come up with the probabilistic version. But instead of dealing with, let's say, 20 obstacles, here we just need to deal with 3 convex sets. Okay, so the next approach that I'm going to look at, it's a chance constraint RRT star. So we all know that how RRT star works. So we are given initial states, we sample the state space, then we keep the obstacle-free samples, then we drive the robot toward these sample points, then we get to the new state, and then we repeat and grow the tree until we get to the goal region. In chance constraint version, so we assume that we are given an initial, we have a linear dynamics and a controller, a predefined controller with fixed gain. For example, we can obtain it from LQR to drive the robot toward the sample points. So, and we are also given an initial distribution for a node. Then since we have a linear dynamics and linear controller, we can propagate this distribution and find the distributions for each node. And instead of looking for obstacle-free node, we are going to look at risk-bounded nodes. By these equations, we are propagating the Gaussian, and then using the disjunctive linear constraint that we discussed, we can immediately calculate the risk of each node and then keep the nodes that satisfies our chance constraint. So at the end, we are going to see a tree like this. We have different distributions on the nodes. So we need to grow this tree until the expected value of the distributions meets the goal region. So here we are just only looking at the distributions on the nodes. We can also find these distributions over the trajectories while we are traveling to the nodes and calculate the risk of the trajectory, not the final node. So next approach is a risk-bounded PRM. So in PRM, so the whole point of PRM is to construct a graph. So instead of working with trees, we want to construct the graph in offline mode. We want to find obstacle-free nodes and connect the nodes with edges and design a controller in offline mode to travel between the nodes. So we want to do all calculation offline, and then in real time, everything reduces to the graph search problem if you want to do motion plan. Now assume that we have uncertainty. Robot is in the node 0, it has an initial distribution. Robot travels to the node J using 2 different paths. So depending on the travel path, we are going to see different distributions for a robot. Is this good or bad? We can get to one point with different distribution. What does it mean? Any thoughts? I can hear you.
Based on the uncertainty, you can choose the path. So you can decide which path to take.
Yeah, in that sense, it's good, but we wanted, so the whole point of the PRM is the graph structure. We want to do the calculation once and then use the results in real-time case. But when this happens, it means that although I have a graph in state space, in the belief space, which is the space of all the distribution, we are going to get a tree. It becomes similar to RRT star. So at each time, if I'm given a distribution, we have to grow a tree, propagate the uncertainties, and repeat the old calculation to find the path. So there is no point to use a PRM if we have uncertainty, right? Do you see this problem? So we want to construct a graph in belief space, not a tree. If we want to work with tree, we can go back and work RRT star. It is shown that if we enhance the constructed graph by 2 sets of controllers, time varying LQG as a edge controller and also a stationary LQG for the node controllers, we can show that we can send a family of Gaussian distribution to a certain family of Gaussian distribution under these controllers. So we can define this family of distribution as a node in my belief space. So these families are going to represent the nodes of the graph in the belief space. So then if robots gets to one node under these controllers, we know that its distribution is part of this family of the distribution in the node. So we don't need to repeat the calculation. We don't need to start from the 0 node and propagate the uncertainties and find the distribution for current node. We can, in offline mode, find these family of the distributions and construct a graph, and then find the risk of for each edge in offline mode. And then in the real time, everything reduces again to a graph search problem in the belief space. There are also many mathematical details on mainly on this convergence. So if you look at the firm techniques, you can find more details. So in the first set of tools, we assume that everything is linear. We have a Gaussian distribution. we have linear obstacles, and we come up with the risk-bounded version of popular planners, RRT star, PRM, and trajectory optimization techniques. Right now, we are going to look at more general cases where we have nonlinear dynamics and arbitrary distribution. Let's first look at the arbitrary uncertainties. One option to deal with this arbitrary uncertainty, in the Gaussian case, so we saw that if distribution are Gaussian, we can replace that probabilistic constraint with a linear constraint based on mean and covariance. If we have non-Gaussian distribution, means that the states of the system are going to have a different distributions. I'm going to use results from distributionally robust techniques. So based on these results, given a linear chance constraint, if the mean and covariance of any distribution, not only Gaussian, any distribution satisfies this linear constraint, then we can satisfy the chance constraint. This new constraint is similar to the Gaussian case. We only have a different safety margin C. In the Gaussian case, safety margin is described as a CDF of the standard normal distribution. But here, safety margin is only based on the risk bound. So if we have a linear dynamics with arbitrary distribution, we can propagate the mean and the covariance in the same formula. And once we get the mean and the covariances, we can use this new linear constraints based on mean and the covariance. And if I plot these new constraints, we are going to get this larger obstacle for arbitrary distribution, because in this case, this linear constraint tries to take care of a huge family of the distributions. So this results in a larger safety margin compared to the Gaussian case. This is the easiest way of handling arbitrary distribution. I will get to this problem at the end, and we will look at a completely different approach. So let's look at a nonlinear system. So what is the easiest way to handle nonlinear system? You all know the answer. Yes, so we can linearize it. But to do this, I need some kind of trajectory first so that we can linearize the dynamics around the trajectories. There is a set of tools, motion planning tools, that in the offline mode, they construct a library of the different motions that we call them motion primitives, library of the different maneuvers. For example, here, these are the different maneuvers for a rover to go in different directions. Or for example, we have a library of the maneuvers for vehicle for merging right and left with different velocities. We can construct these motion primitives by considering the nonlinear dynamics of the robot. By building this library in the online mode, we only need to find the right maneuver to execute, or we need to look at the right sequence of these maneuvers to get to the goal region. When we have an uncertainty, and instead of looking for optimal maneuver to execute, we can look for risk-bounded maneuver. So for this, we are given a library of the motion primitives. We can linearize the nonlinear dynamics around these trajectories using the Taylor expansion. So we are going to get a linear dynamics. So we know how to propagate the uncertainty. We need to propagate the mean and covariance. For example, these are the propagated uncertainties along the trajectory for the vehicle. This shows the sequence of the Gaussian distribution along each maneuver. Then we know that, so given these sequence of the distribution, we can use disjunctive constraints to calculate the risk of collision with obstacles, right? So for example, we use these disjunctive constraints given the linear obstacles to calculate the risk of each maneuver. For example, in this scenario, we have two vehicles, and I have two set of maneuvers for keeping the lane and changing the lane for the blue car. This car, at each time k, calculates the risk of each maneuver. And when the risk of keeping the lane increases, it happens when it gets close to the red vehicle. When the risk of that maneuver increases, it decides to change lane and execute a different maneuver. Okay. The next approach, I call it risk-bounded control, and the main idea is that we first assume that we have no uncertainties. We have a deterministic nonlinear system, and we use the nonlinear trajectory optimization techniques that you saw on Tuesday, and we come up with a nominal trajectory for the plane. And then we want to design a controller to minimize these deviations because of the uncertainty. So here I don't have a chance constraint. I just want to minimize the risk of collision with obstacles. I want to minimize the risk of the execution of this given maneuver. Any closed-loop controller will minimize this deviation. So LQR controller is one of the popular closed-loop controllers. So let's see how does it work under uncertainty. So we are given a nominal trajectory by solving the nonlinear trajectory optimization. Then we are going to, again, linearize the nonlinear dynamics around the trajectory. So we are going to have a linear dynamics. In the deterministic case, LQR tries to minimize this given quadratic cost function. And in the stochastic case, it tries to minimize the expected value of the given cost function. Surprisingly, LQR offers us the same control input for both deterministic and the stochastic case. It gives us this feedback that gain is obtained by solving the Riccati equations that comes from the dynamic programming. So simply, LQR controller doesn't care about uncertainty, even if we ask for. This is terrible in some sense, but in other sense, it is good and makes life easier. This is called separation principle in control, meaning that we can separate the process of designing a controller for a linear dynamics and the process of designing a state estimator to deal with uncertainties. While we are designing a controller, we don't need to care about uncertainties, and while we are designing a state estimator to deal with uncertainty, we don't need to worry about the controller. We can design them separately and then mix them and get a LQG controller. So in that sense, this is good. The main reason that LQR gives us the same control is that we are trying to minimize the expected value. So to avoid this, the other option is, instead of minimizing the expected value, I'm going to minimize the covariance. So what does it mean? So because of the uncertainty, we saw that at each time k, we have states has a Gaussian distribution. So we have a vector of Gaussian distribution. And I want to minimize the covariance of the joint Gaussian distribution of this random vector. So we are going to look at feedback controller to minimize the covariance with respect to some constraints on controller. In here, we can assume some kind of control actuation, but in the LQR case, we don't have any constraints on the control. LQR assumes that we have unbounded control input. But here, we are allowed to consider constraints on the controller. Now, it is shown that this covariance, defined as here, is equal to the maximum eigenvalue of this matrix constructed by the parameters of the linear dynamics, unknown gains, and also stack matrix Mi. So to minimize covariance, we need to minimize the maximum eigenvalue of this matrix with respect to this linear matrix inequalities. So it means that we need to look for some positive semi-definite matrix. It means that all eigenvalues of this matrix should be positive. This problem is convex, and we can solve it efficiently by doing eigenvalue decomposition. And we can solve them efficiently by mosaic or Sadumi solvers. These are LMI-based or semi-definite programs. So by solving this convex problem, we can find a gain to minimize the covariance and see, let's see how it works. This is the propagated uncertainty under the regular feedback, PID. And this is the uncertainties under the covariance minimization. And it makes a lot of difference if you consider it with the PID. And for this scenario, we can avoid the obstacle by just minimizing the covariance, or at least we can reduce the chance of collision. So I define the covariance in here. So if consider that vector of the Gaussian random variables, each represent the states of the system. So then we are going to have one matrix for covariance. We have a covariance matrix. So we want to minimize. So in other sense, we want to minimize the covariance of each of these uncertainties along the path to minimize the deviation. And it is shown that to do this, we need to look at the eigenvalues of this constraint in terms of the parameters of the system. Okay, any other question? So in the previous approach, so I wanted to compare with the deterministic trajectory optimization. Deterministic trajectory optimization, we look for some open loop controllers. Okay? So that's why I was in the chance constant optimization, I was looking for some open loop nominal trajectories. But we can also look at the same time for some controllers and the nominal. But in that case, we are going to see a nonlinear optimization. We are no longer going to get a convex optimization. But the other option is that we design a controller. Let's say we design an LQR controller offline, and then we plug that controller into the system. So we get a closed form system, and then look for the open loop nominal trajectories to minimize the risk. By choosing so if we get back, yeah, so the deterministic version of the trajectory optimization is stochastic. So we are looking for the sequence of the U's. So if I want to consider controller, I can design a controller, and then in this case, the U would be KX states feedback plus the open loop controllers. I get the K from, let's say, LQR, and then look for the U stars by solving this optimization problem. Or we can look at the same time for the controller and the open loop, but then we will going to get a non-convex optimization problem. Okay, the last approach. So far, you saw that the main idea was that first represent the distribution with the mean and the covariance, and then replace the probabilistic constraints with linear disjunctive constraint in terms of the mean and the covariance of the distribution. But this time, I assume that we are given in nonlinear dynamics, arbitrary distribution, non-convex obstacles. I'm going to represent the distribution at each time with higher order statistics of the distribution, where I call it moment. We are going to see the definition of the moments. And then I will replace the chance constraints with linear matrix inequality in terms of the moment. So we know that what is LMI. We saw that in the previous approach, some linear matrix inequality. So first, let's see what is moment. So for a given distribution, moment is described as this expected value. So the moment of order alpha is the expected value of the x to the power of alpha. So what is first order moment? Moment of order 1, where alpha is 1. Mean, yes. So, and similarly, the moment of order 2 is variance. So indeed, in the previous approaches, I was using the first and second order moments to describe the distribution, but here I'm going to use a higher order moments. I'm going to use first moments, second moments, third, and until to some fixed order moments. So I'm going to use this vector of moments, this vector of higher order statistics to parameterize, to represent the distribution, and then I'm going to find a new deterministic constraint on these moments to satisfy my chance constraints. We can retrieve all information of the probability distribution given the moment sequence. So let's see how moment and probability distributions are connected. Given a probability distribution, if we find the inverse Fourier transform, which is also called a characteristic function, and then if you find a Taylor expansion, we are going to observe the moments. Moments are coefficients of Taylor expansion of inverse Fourier transform of the probability distribution. This is how they are mathematically connected. But I'm not going to use these equations to solve my optimization. So, in summary, we are given a nonlinear dynamics. I don't want to linearize it. We are given arbitrary distribution. I don't want to assume that they are Gaussian. And we are given non-convex obstacles and non-convex goal region. I don't want to approximate them with the convex regions. So the goal is to find a controller. Here, this controller could be both open loop and a closed loop. I want to find these controllers to maximize the probability of success. The success here is defined as probability of remaining in the safe region at each time, and also getting to the goal region. With respect to these dynamical constraints. So my only assumption is that all functions are polynomials. I have a polynomial to describe my dynamics. I have a polynomial inequalities to describe my obstacles and also goal region. Then we need to solve this probability maximization in terms of the given probabilities. Now, using the given dynamics, I can express it at each time xk in terms of the given control inputs and the initial states and uncertainties. By using this description for xk's, and if we plug them inside my probability of a success, we are going to get the probability in terms of the polynomial of the obstacles and polynomial of the dynamics. I want to clean this statement and come up with the new one. I represent all polynomials with one polynomial pk, which comes from the polynomials of the obstacles and the dynamics. And I define a new vector A, which is our decision vector, which is in terms of the control inputs. And I define uncertainty vector Q, which is a vector of all uncertainties, uncertain initial state and uncertain parameters. Then we can rewrite this optimization in terms of this new definition. This is the standard way of representing probabilistic optimization. I'm looking for a control decision to maximize the probability of the success defined in terms of the uncertainty and decision variables. Now, we can show that to solve this problem, we need to solve this LMI in moment space. It looks ugly, but these are convex problems and we can solve them efficiently. Based on this problem, we need to look for two set of moments represented by y and a to satisfy these linear matrix inequalities. The M matrix, it is called moment matrix, and Lm is localizing matrix. Moment matrix is defined in terms of the moments, and it's a symmetric matrix. For example, it shows an example for a moment matrix of order 4, where it used the moments up to order 4. Now, if this matrix is positive semi-definite, meaning that if the eigenvalues of this matrix is positive, we can claim that the given vector y are moment sequence of some probability distributions. Next, localizing matrix. Localizing matrix is defined in terms of the moments and given polynomial. Now, if this localizing matrix is positive semi-definite, we can claim that the probability distribution of the moments y are defined on the region described by the given polynomial pk. So if this region describes our safe region, if we satisfy this, means that the probability distribution of the states are defined in the safe region. So this is how we can avoid the obstacles, by satisfying this linear matrix inequality. So in summary, these LMIs make sure that we are looking for moment of sequence for probability distributions that are dynamically feasible and also defined in, and they are defined in the safe region so that we can avoid the obstacles. And now the main term is this: as we increase d, d is the number of the moments that I use to parameterize my probability distribution. And as I use more moments to describe my distribution, the cost function of my optimization will converge to the probability of the success, the probability of the original problem. And also the zero order moments of the second vector will converge to my controller. So this is exactly what we were looking for. So by increasing the d, we can get to the controller that works for nonlinear dynamics, arbitrary distribution, non-convex region. And how many of you know about sums of squares techniques? Okay, each optimization problem has a dual problem. If we take the dual, we will see that we will get to the sums of squares problem. It turns out that looking for moments of probability distribution is equivalent of looking for some positive polynomials. So we can reformulate this problem as a sums of squares problem. There are many mathematical details behind these techniques. It requires functional analysis and measure theories. To get more information and see how these problems are connected, sums of squares and these LMIs, and how we can improve the convergence rate for this problem, please look at my papers, and if you have any questions, we can discuss more. Okay. Only one thing, the main problem of this approach, this LMI-based approach, although these are convex problems, they can easily get intractable as the size of the original problem increases. So if the size of the original problem increases, we need to solve the LMI problem with larger matrices. So this is why it can get intractable. So, and to be able to handle large problems, we need to look for some kind of sparsity or structures in the matrices so that we can reduce them with some small matrices. So let's wrap up. But before that, there are some remaining points. Throughout this lecture, I assume that we are only given a state space model that describes my robot. We can also have observation model. When we are given an observation model that describes the behavior of the sensor, we only need to come up with the new equations to find the probability distribution of the states. To do that, we can use a Kalman or extended Kalman filter if we have access to observation. What do I mean by this? If we are at time k and I want to plan for a future finite horizon, I don't have access to my future observations. So future observations are random. In this case, we can use LQGMP approach that modifies the Kalman equations and find the new way of calculating the uncertainties. Next, I assume that my states are continuous. We didn't look at discrete space. In discrete space, the problem is much, much easier. We have a discrete finite set of states, and instead of a continuous state model, we are given state transition observation matrices. And by multiplying these matrices, we can find the discrete probability distributions of the state. And given these discrete distribution, risk reduces to some sum with respect to the discrete distribution. So we don't have the problem of uncertainty propagation and the calculated integrals over the non-convex region. To find the risk-bounded controller, we can actually look at the constraints POM-DPs. We can use constraint dynamic programming, or we can use heuristic tree search techniques. Okay. So in summary, we saw that we need risk-bounded planning techniques to first deal with uncertainty and next to get less conservative solutions. And we show that this problem is all about shaping the probability distributions of the states so that the overlap of the distribution with the obstacles becomes less than the risk bound. And to handle this, the main idea was that first replace the probabilistic constraints with deterministic linear constraint in terms of the mean and the covariance. And in the more general case, we first represented the distribution with higher order statistics and then replace the chance constraint in terms of some linear matrix inequalities. But before I finish my talk, I want to ask you a question. We all know about risk-bounded techniques for planning. So are you willing to take risk giving this information? Risk in your research, work, or in your life? Let me give you a scenario. So assume that we are requesting a Lyft or Uber ride, and the app shows the risk of that ride. For example, it tells that, okay, this ride has a risk of 0.01. This is the chance of failure for the ride. How many of you are willing to take this risk and accept the ride? How many yes answers? And how many no answers? Yes, this is the right answer. The right answer is not yes or no. The right answer is that how do I define the risk for this scenario? What is failure? If this failure means that, for example, the driver is drunk and we are going to have a fatal crash, my answer is no. And I don't care how many zero you put behind the one. I'm not going to take this risk. But if this failure means that, okay, we are going to get 5 or 10 minutes late, then I can look at this number and decide. So before we use chance constraint techniques, we have to know what is the definition of failure. We have to know what are the consequences of the failure, and we need to plan for that cases. So in this talk, I suggested to use chance constraints approach, but maybe the right solution is to first we use robust techniques to limit the consequence of the failure, and then we use chance constraint techniques on top of it, so that we can get more solid techniques. Okay, any question?
What do you mean by robust techniques?
So at the beginning, I said in robust techniques, we only look at the uncertainty set. The obtained plan should work for all values of the uncertainty.
Yeah.
So it results in two conservative approach. But in the probabilistic version, not only we look for the uncertainty set, we also look at the probability distribution.
Okay, so when you say look at robust techniques for failure, you
conservative for that scenario, but for the, let's say, traffic scenarios, we can act with more freedom using this responded cases.
How do you choose the parameters of the model after you define it?
So the model, we assume that we are given a state space model. So we have the model. But for the model, the uncertainty, if you mean, so by observe, so in the so in this slide, okay, so we saw that by observing the uncertainty, if you look at the samples, we can use some kind of numerical techniques to find the distributions. We can use these techniques to find the probability distribution of the just uncertainties, not the state itself. So we need data and observation in general.
So, I think what you said was like whenever disaster, should go for a robust approach and
This is my opinion. If you are willing to take this,
isn't it when we so in the bounded approach like for this if we consider the bound very large, are we going to
if you have an unbounded uncertainty, if you mean, so we can actually use robust approaches. We have to go for Gaussian representation of the unbounded techniques. Or we come up with some kind of approximation of this kind with bounded uncertainty.
So in the end, when you mentioned nonlinear state transitions, you assume that it's a polynomial.
Yeah.
But what happens if you cannot model it as a polynomial?
So usually in robotics, we see sine and cosine terms. So what I do, I find the Taylor expansion up to order 3 and it works.
Can you go back to the, can you explain the family of Gaussian approach that you had for the PRM? So like the specific thing that I did not understand was do we not have to calculate for us to get the propagated uncertainty at every Gaussian measurement? Are we proposing that we do not have to calculate that, or are we saying that that can be done?
So I'm saying that, yeah, so if we construct the graph in belief space, we don't need to propagate Ashkan. So when robot brings to a node, we know that its distribution is part of the family of the distribution that construct that node. So this is the whole point of the Prm approach. We don't need to repeat calculation at each time. We only need to do all calculation in offline mode and then use the results in the real time. Any other question?
I think the data available is often limited compared to the size of the state space. How would you reliably estimate parameters from especially for driving application?
Yeah, so in my techniques, I always assume that we are given some kind of probability for uncertainty. So I haven't looked at actually explore these techniques. But the main approach is still using the data. So we have to study, observe. So, but in practice, everyone assumes that there is some kind of Gaussian distribution. Okay.
So I was thinking about the comment that you made at the end about robust control, right? Which I highly disagree with. But I wanted to understand what you're saying. So the thing in a robust control approach is if you do have unbounded uncertainty, right? Then in the robust control, you're still going to pick some set. And then you're going to say, I'm going to count for everything in that set, and everything outside that set, I'm going to pretend
But when we are originally want to deal with bounded uncertainty, in practice this is the case. We have a limited energy, so we are going to have a limited bounded uncertainty. And for that case, I was comparing using robust techniques for bounded scenario with the probabilistic version. This probabilistic version results are less conservative. But we have to be prepared for failure.
So I kind of understand the underlying equation, right? So are you saying that often what we want to do is to do risk minimization, or the extreme is what I do is I mainly try to be as safe as possible, but then there are certain places where it's worth taking risk because there's utility, or you have to take risk?
Yeah.
Is that what you're arguing?
Yeah, some kind of.
So I'm just wondering, I mean, so it is, you know, a concern with chance constraint approaches is that when you say that you have to be safe 90% of the time, the algorithm says I can fail 10% of the time.
Right.
Now what it'll do is it'll maximize utility, right? But there is the idea that a good algorithm spends the 10%, even though increasing the risk by 10% may only give you a 0.01 improvement in terms of utility, right? So there is this notion of if you're going to take risk, then you really want to get significant benefit in the utility, which you're not getting here. Now, it seems to me you're perhaps saying first and foremost, try to be safe. And then there are certain periods where you will actually consider taking risk.
Right. Because all the literatures just talk about, okay, let's take risk and get less conservative. No one talks about the failure. What if you fail? We should be ready for what comes after failure. So you have a plan B, not trust mechanisms.
All the evidence.
So your last name means brave, right?
Right.
That's why you're working on risk-bounded case. You're brave
Maybe.
enough to take risk. Is it?
Yeah. I'm not sure.
It's a joke.
Okay, I guess.
Okay, good. So we're going to break for lunch, right? And then at 1 o'clock, go back to the lab, and we'll give you the chance. Okay. Thank you all for joining us for the week. It's been great to have you here.
Thank you. Thank you.
I really liked your talk.
Thank you.
I have some questions on. I think it'll be useful to look at the presentation.
Okay.
Maybe we can do it somewhere. I really like all your visualizations. They're so nice.
Thank you.
So there was one graph where you were comparing different delta values. I wanted to get an understanding of how is that delta related with the risk that.
So this.
Oh yeah.
This is the overall risk for the mission. This delta. So we want to risk this amount from time 0 to the end of the mission.
Okay.
Then we have t times that.
Right.
So we can find the amount of risk for each different time.
Okay.
So then you can solve the optimization where I needed this delta case.
Okay. So if in this graph, this delta directly corresponds to the risk, the final overall risk. So in this case, when delta was 0.1, which means that the risk was less. So it took this path.
Yeah,
but
it's closer to the obstacles. We have
but-
a chance of.
yes, and then when the delta was very small, which means the risk is very less.
Right.
Why did it take this path?
So as you see that we have a safety margins. So the chance constraints introduce a safety margins around obstacle.
Okay.
This this safety margin is a function of my risk bound. Safety margin with
Oh, it is 1 minus. Oh.
so
Okay.
as the
Oh yeah, as the delta increases, this
The safety margin increases, it blocks this path,
Okay.
and then from the chance point of view, there is no path, so you choose the other one.
But in the example that we tried to motivate the entire our risk bounded versus the robust techniques.
What's that?
The example where we were looking at robust techniques versus risk bounded systems, where as the risk increases, right,
So
it goes
so
into a
in
failure.
In the first example, when I compared,
Yeah, this one.
so in here, for example, when risk increases, it means that there is a high chance of observing obstacle.
In this one. Oh yeah, this one. Oh, sorry. Okay. So in this case, the risk has.
Here, so here I have in here, risk is 0.
Right. If the risk is 0, so it took this path,
Yes.
which
so
means delta is 0 in this case. So
Yeah.
it took this path. Okay.
But yeah.
Okay, and by means of uncertainty, doesn't mean that it's possible that the robot is not fully follow the path, so that it is possible to calculation. What is the meaning of uncertainty in this?
So in this problem, uncertainty comes from the environment.
Okay.
So, but the robot itself, for this example, is deterministic. So I want to.
And
But in general, the old technique is for the case that there is uncertainty. So if it follows the given path,
yeah,
we are like the airplane scenario. We are going to see deviations
okay.
like this because of the uncertainty.
Okay, so are you working on some model like this, like more complicated, more realistic? Like you are modeling the real life traffic, the driver experience the uncertainty from the outside experiment and uncertainty of the driving system. So then come the risk. Do you model like?
So actually, what we are doing for that case, we assume that as I said, the intention of the other vehicles are uncertain.
Yeah.
So at each time K, there is a distribution for their behavior. With some probability, they may merge right, left, or different acts.
Yeah.
It comes from the intention recognition process. It outputs the probability of each action.
Yes.
Then, by using this probability, then we can calculate the risk for our maneuvers.
Okay, I see.
So if I go forward, what's the probability that it merges left and we collide?
Okay. Yeah.
So it requires another set of skills for the prediction, probabilistic prediction for the other vehicles.
Yes, got it. So is there some paper you are working on that can
For the intention part or in general?
like the intention part and action?
So I haven't put the intention parts here, but for all techniques I introduced the papers in the beginning, so we can find these papers for each of these techniques. But for the intention part, actually, I can send it to you if you want to.
Okay, that would be great. And also, that is a small question. You mentioned minimize the covariance.
Oh yeah.
Yeah. So could you go to that slide? I think it's here. Yeah. So maybe here. So why do you want to minimize covariance? I mean, is that related to minimize the mean square error? Or is that related?
No, so it's compared with LQR. In the LQR, we want to minimize the expected value of
Yeah.
this function. So when we are doing this, it gives us the same control and simply doesn't care about uncertainties.
Okay. Yeah.
So I said, okay, let's directly minimize the deviation, this deviation,
Yes.
and I represent this deviation. I measure this deviation with the covariance,
Okay. Yes.
so which is shown here. These are the covariance of the uncertainty.
Okay.
So by minimizing this covariance, I can minimize the deviation.
Okay. Yeah. So is that like you are in this way you minimize the uncertainty?
Yes, I want to try exactly uncertainty. Yeah, uncertainty that comes from propagation. Exactly. So if let's say we get a zero covariance, then problem becomes deterministic. There is no
Yes.
uncertainty.
Yeah.
So in this, for getting this trajectory and the uncertainty that has propagated throughout this trajectory. We are looking at the vehicle's process model, the process model.
The dynamic is given, maneuver is given, and just propagating to the state.
And there is no information about observations from the environment. This is an open loop.
I haven't considered observation.
And this is also in a similar situation. So I'm quite curious because in general, in order for going from here to here, we consider observations from the environment, and after doing a lot of optimization, we finally end up.
Another option, but when so to reduce the uncertainty, we usually use some kind of landmarks.
Yes.
But when I'm driving in the let's say
completely unknown.
Yeah, no environment. I don't have any landmarks, so we have to look for different approaches.
So, and this is quite comparable to a situation where even if you take measurements from the environment,
I haven't compared to see which one actually reduces uncertainty more. But I can only compare these.
I'm quite amazed by the fact that you're able to go from here to here with just the state model.
Isn't it because the expected value is actually going to be the trajectory when we're trying to solve it?
Always.
So that's why the LQR doesn't work in these cases, because we're not actually trying to solve anything new.
We are trying to minimize the uncertainty. If you do not...
When we're actually using the expected value of it, it's just the mean, right? So mean would be the actual...
But it's not the mean that is important. It is also the covariance that builds up.
That's why this approach makes sense and this doesn't.
Yeah.
Because like this was not actually trying to do anything new.
Yeah.
That's right. That's right. Yeah, it only considers expected value and doesn't care about the covariance.
I also had another.
Sorry, that's a good point. I have to actually compare and see observation these techniques.
And also, I had another question, which is maybe I'm missing some information. So every time when you were propagating the uncertainty, you were only looking at the previous step or the entire part.
This is what happens if you write the equations. This is going to in the state space model.
Right.
This is happening.
And then even when you were even in this case, you were also looking at only the previous state, or were you looking at the entire?
I'm just looking at the
previous state.
So I'm using the same equation to propagate the uncertainty.
Wow. Okay.
This is the case for all the dynamics.
But would it be interesting? But would it be interesting to look at the entire path?
Why should I do that?
Because if you only look at the previous step,
then I can get all information by just looking. So why should I?
Oh, you're getting all the information about the previous path by looking at the previous step.
So based on the state space model, to get the information of the current for my current time, I only need to look at the previous time. I don't need to look at the history. This is the whole point of state space representation.
Yeah, but then when we solve for say some factor graph model, in general, like a regular factor graph. When you write it down as a nonlinear least squares solution, in general, in order to get this sort of a trajectory at the end, it is required to look at the entire path.
If you want to solve the dynamics, your solution actually is going to start from the first place.
Right.
But we can, instead of doing that, we can only look at the dynamic itself. The whole point of the state space is this. Instead of looking at the history, we want to look at the short time behavior of the dynamical system, and then we judge how it's going to behave.
Yeah, maybe I'm a little confused on why we use a nonlinear least square solution versus Kalman filtering. I'll look it up by myself. Right.
So send me an email if you.
Yeah, sure. And sorry, if anyone has questions, please.
PRM. It's not all possible approach. So we design. So actually, it comes from this convergence property of the linear controller. So we construct a family of the controllers. Then we can give. Let's say this is given. Then under this controller, we can come up with this convergence, and then if we keep repeating this over the graph, we can construct the family of the distribution as a node once in offline. Okay? Then it means that if robot travels under this controller, at each node, its distribution is already calculated. It's inside this family of the distributions.
I see. So you pick a max covariance from.
So this is a family of distributions, a different distribution with different means and different covariance. So it is described by this a distribution. Let's say the mean less than the node. This is the node less than sum, and also the covariance less than sum.
Oh, I see.
So this is a continuous set of distributions.
So
it's a ball. In the belief space, it becomes a ball. This is how I represent it.
So when you compute the risk as this node, you pick the worst case.
Yeah. So I'm considering all the distributions. So it gives it's overestimating the risk. It's some approximation of the risk. Okay. Yeah.
Like the safety margin we're considering because like we know the map already for sure, right? We only have uncertainty in our
Yeah,
system.
for this scenario.
Then like as we propagate our model, our uncertainty increases, right?
Right.
So shouldn't the safety margin be less for closer objects and more for farther objects? Because as uncertainty changes, even the safety.
So this safety margin puts the condition. It shows the safe region for the expected value, the center of the circle. So we don't care actually how far we are. It only so let's say my expected value can be somewhere in here. So in this case, it satisfies my safety constraint. So its safety constraint be somewhere outside this line, and only depends on the size of the uncertainty, which is the covariance. So we don't care how we are close to the obstacles.
How do we pick the safety margin?
So it comes from these equations. I first started with the deterministic case, then come up with the probabilistic case, and then I show that to satisfy this probability constraint, if you write the equations, all comes from here. If you use this result, we are going to get this new linear constraint in terms of the mean and in terms of the covariance. I call this new term C the safety margin. So it comes from the equation. We don't pick them.
So the delta K is
Risk at time K. It shows the risk at time K, and it appears in the so safety margin relates to the covariance of the states and the safety bound, so the risk bound.
So delta K over time.
What's
Okay,
that?
so including the covariance would actually, like the problem which I was saying, so including the covariance would solve it, right? Would actually be changing the C for farther objects.
Yeah. So at each time covariance changes, obstacles increases.
So this is done offline.
This is the optimization, so we have to solve it offline. But since it is linear, we can instantly solve it.
Like for LQR, you are computer feedback key offline, and the delta K is changing.
So in the LQR case, actually, so we don't have any delta case because we don't have any risk bound. So what I did, I assumed that so we are given a nominal trajectory, so we can actually deal with chance constant. We only can minimize the risk. We don't have any risk bound.
Yeah, I have one question, which is probably a little bit philosophical. At the end, you said we should always have a backup plan, a safe plan, a robust plan. But when we look at the example where a car overtakes the other car, there can always be, there's always the possibility that the front car is moving sideways, for example, when you try to overtake.
Right.
It depends on the intention model probably, that you,
Yeah.
how you model it. But essentially, if you reduce risk to zero, you would never be able to overtake. It's just the consequence.
Right.
Right?
Yeah, that's true. Yeah, but for the vehicle case, so almost all the literature considers some kind of robust techniques. Some
Would be able to brake or,
yeah, some
or to steer away.
Lyapunov kind techniques that they want to actually get the zero chance of collision. So they don't. So if you want
So
to
they
use
have a
it-
dynamic model of.
yeah, they are too
okay.
conservative, so
Yeah.
they don't even approach the vehicles. So they stay far,
Yeah.
such that no matter how they behave,
Okay.
we are not going to collide.
And the risk is reduced, or the bounds are
Yeah,
reduced
it's zero
the
for
faster you go, for example.
Yeah, for those approaches, zero.
Yeah, okay.
But my argument is that so this might become too conservative, so maybe we can do risk and get some more freedom
Yeah.
to create some complex maneuvers.
Because we start working similar example. It's mobile manipulators, and we're not allowed to touch or collide with humans. And the problem is how to model humans.
Yeah.
They could
Yeah.
any second they can jump
Right.
left or
The-
right. It's not possible.
So yeah, we are using these techniques using the intent recognition. So it's used completely different approaches. It actually sends us the probability distributions for each available action for human. So what is the probability that right now, for example, I raise my right hand or this.
Yeah.
So we first calculate these probabilities and then use those probabilities to calculate the risk.
Okay.
Of the maneuver. Yes.
Can you point at the publication probably regarding human intention modeling?
Oh, yeah, I can. I don't have them here, but like, if you send
I
me
send you
an
mail.
Yeah, send me.
Yeah.
Remind me.
Thanks.
Hello. I'm PhD from National University of Singapore. I'm working on actually autonomous driving based on intentions. So actually, in terms of the risk-bounded maneuvers, I have some problem. First, how do you define the maneuvers?
Okay, so as I said, so in the offline step. In the offline step, so based on so let's say I use trajectory optimization.
Yeah.
I define, or we can use Dobbin's curves. So
So
these
basically-
are the different maneuvers. It gives me the control inputs
Okay.
to see this maneuver. Velocity, acceleration.
It's
steering angle.
basically a fixed trajectory, right?
Yeah, it's a fixed trajectory.
Okay. Then the second question is if you do this. Oh, sorry.